Testing one, two, three. Testing one, two, three. Hello, everyone, and welcome to Inductors, Energy in a Magnetic Field. We will be covering Chapter 13, Principles of Electric Circuits, Conventional Current. My name is Professor Vasquez, and welcome back to Magnetic Minds, where we bring electricity to life, one concept at a time. Again, today we kick off Chapter 13 of Principles of Electric Circuits, and it's time to meet a component that quietly controls current, it stores energy, and resists sudden changes. That is, our friend the inductor. If you've ever wondered how a transformer works, how motors regulate themselves, or how switching power supplies stay stable, inductors are in the middle of it all. In this chapter, we're going to cover what inductors are and how they store energy in a magnetic field, how they oppose changes in current, and why that matters. Key characteristics like inductance, time constant, and energy storage. Practical uses like filters, chokes, timers, and power electronics. We're also going to cover series and parallel inductor combinations, and don't forget Lenz's law and electromagnetic responses, and how inductors interact with resistors and capacitors in RL and RLC circuits. So from coiled wire to complex circuit behavior, inductors give us a control over current in a way no other component can. And this is the magnetic sibling to the capacitor and a vital part of your electrical engineering toolbox, as we mentioned before. So let's go ahead and dive in. Again, I'm Professor Vasquez, and this is Chapter 13, Inductors. All right, everyone, inductance, resisting the rush. Let's start at the core, literally, of what an inductor does. And what it does is it resists change. Inductance is a property of a conductor, usually coiled, and that causes it to oppose changes in current. It's not about stopping current altogether. It's about pushing back when that current tries to change too fast. So when current flows through a conductor, it produces a magnetic field around it. If you form that conductor into a coil, like the one on the left side of the slide, that magnetic field line reinforces each other and the concentrating field inside that coil. And this makes that coil behave like a magnetic device, like a bar magnet. And if you wind that coil around a magnetic material, let's say iron or ferrite, you greatly magnify the effect. So more magnetic field, more inductance. And here are the key concepts to pull from this. When you try to increase the current, the coil builds a magnetic field. That changing field induces a voltage that opposes that increase. So when you try to decrease the current, that field collapses, again inducing a voltage, but this time it opposes that drop. So this behavior is a direct consequence of Lenz's law and Faraday's law of induction. So in essence, inductance is a kind of inertia for current. Just like mass resists changes in motion, inductance resists changes in current. And that's why inductors are used to filter, they're used to smooth signals, they store energy in switching power supplies, and they help shape timing in analog circuits. So let's go ahead and continue with the next topic. Ooh. All right, everybody, let's move on to self-inductance, a coil that fights its own current. You might think of this as a coil that needs some therapy, right? A little joke there. We've talked about inductance as a concept, but now let's look at its mathematical form, self-inductance. Self-inductance, usually just called inductance, it's the property of a coil to oppose changes in its own current. It's not about interaction with other coils, that's mutual inductance. This is a coil resisting itself. The unit of inductance is called the Henry, and we symbolize that with the symbol H, or the letter H. And here's a definition. A coil has an inductance of 1 Henry if a current that changes at 1 ampere per second induces a voltage of 1 volt across the coil. The simple idea, or the deep consequence, um, the key to the equation for induced voltage is that you have an induced voltage equal to the inductance designated by L times the difference in current over time, or dIdt, for those of you who enjoy calculus like I do. So induced voltage, V sub I and D, is the induced voltage in volts, L is the inductance in Henrys, and dIdt is the rate of change of current in amps per second. Right? This equation is central to understanding how inductors behave in time-varying circuits. If current is steady, no voltage is induced. If current is rising or falling, the coil resists with an induced voltage opposite of the change, thanks to Lenz's law. Well, we can explain it through Lenz's law. It's not that Lenz's law creates this. So if you're working with switching circuits, pulse generators, or high-speed current changes, you'll need to factor in this induced voltage. It can protect, it can oppose, or it can even destroy your components if not properly accounted for. Okay, on this slide, we're going to talk about calculating inductance, putting L to work. Now that we've explored the concept of self-inductance and the equation V is equal to L times dIdt, or the rate of change of current, let's put it into practice with a real-world example. So here's a setup. A voltage of 10.3 millivolts is induced across a coil. The current through that coil is changing at a rate of 680 milliamps per second, and we want to find the coil's inductance. Using the rearranged form of the self-inductance equation, L is equal to V induced divided by di dt. So all we got to do now is plug in the values. So L is equal to 10.3 millivolts divided by 680 milliamps per second. That gives us 15.1 millihenries. So this coil has an inductance of 15.1 millihenries, a typical value for signal filtering or transient suppression. Now, here's the follow-up question. What happens if the rate of change of current increases? Well, that's simple. The induced voltage will increase, and it will also do so in an opposing direction, so opposing the change in current. And that's the classic Lenz's law in action. Inductors fight back harder the faster you try to change the current. If you've ever, if you've ever had a stubborn partner, yeah, you know what that feels like. The electrical shock absorbers, basically, if we're looking at it from opposing motion, right? This example highlights why inductors are crucial in, again, power electronics for smoothing and filtering out energy storage, signal conditioning, I'm sorry, and this is to filter sudden changes, and timing circuits where the rate of change actually matters more than the static value. All right, now coils and cores. What's inside an inductor? We've covered what inductors do. Now let's talk about how they're built and what their physical makeup tells us about their performance. An inductor is, at its most basic, a coil of wire, but what's inside that coil, its core, matters a lot. So the core is the material around which the coil is wound, and it can be air or just empty space, a magnetic material like iron, ferrite, or steel, or even an adjustable mechanism, as in variable inductors. And the purpose of that core? To guide and concentrate the magnetic field, which increases the inductance. So let's look at the symbols shown on the slide. So first we have the air core. So there's no core material. It's just a wire coil, a coil of wire. That has a lower inductance, and those are used in high frequency RF circuits where magnetic losses must be minimized. Um, then we have the iron core next to it, iron or steel, and this increases inductance significantly. These are common in power inductors and low frequency filters. Next to that, we have the ferrite core, and that's made from ceramic plus some iron compound. These are efficient at higher frequencies. They're ideal for transformers in switch mode power supplies, and they minimize what are called eddy currents. And we'll discuss eddy currents later in this course or in this podcast, excuse me. And then we have what you see there, the variable inductor. Now, this has a mechanical adjustment. It lets you tune the inductance. These are used in radios and filter circuits where precision tuning is needed. Each core material gives the inductor a different magnetic permeability, and that affects one, the amount of energy stored, the frequency range it works best in, and its resistance to saturation under high current. So the next time you see a coil on a schematic, check its symbol. It's telling you exactly what kind of performance to expect. So, what shapes inductance? Let's look at four key factors, right? So, let's say you've got a coil, but how much inductance does it actually have? The answer comes down to four physical characteristics that directly influence a coil's ability to, again, store energy and oppose changes in current. So let's walk through the formula shown on the slide here. On the slide, we see that we have L is equal to N squared times mu times A divided by L, where L is the inductance in henries, N is the number of turns in the wire, mu, that little mu is the permeability of the core material. Again, this should be reviewed, nothing new. And then A is the cross-sectional area of the core in square meters. Again, for your calculations, make sure that you convert everything to meters if they give you something in millimeters. And then L is the length of the coil, and again, that is also in meters. So let's go ahead and break that down even further. More turns equals more inductance because each loop of wire contributes to the total magnetic field, and inductance increases with N squared, and that's a squared relationship. Higher permeability, mu, equals stronger magnetic effects. So materials like iron or ferrite have a way higher permeability than air, meaning they can channel magnetic flux much more efficiently. Then you have a larger area. So that equals more magnetic flux. The thicker core gathers more field lines. That leads to greater energy storage. And what if you have a longer coil? That actually equals to lower inductance. So as the coil stretches out, the magnetic field becomes rather weak per turn, and it reduces the overall inductance. If you can't remember all these definitions, if you can at least remember the formula, you can at least understand the relationship mathematically. But the bottom line is inductance is the result of geometry and material. That's why high performance inductors are carefully wound with hundreds of turns, compact dimensions, and optimized magnetic cores. And some cores can increase inductance thousands of times over in an air core. And one little thing that irks me is that we remove geometry from high schools, and this is a good reason why we need geometry back in high schools. But I won't get into that in this lecture. I'll do some separate podcasts for why I feel geometry and trigonometry are extremely important for engineering. All right, on this slide, we're going to look at calculating inductance, the math behind a magnetism. So now that we've introduced the formula for inductance, let's walk through a real calculation using actual dimensions and material properties. So the problem here says you're given a coil that's 2 centimeters long or 0.02 meters. Remember, we have to convert everything to the standard unit, which is meters. If you forget to do that, your calculations are going to be way off by decimal points. Again, it says it has 150 turns, is wound around a low carbon steel core, and the core diameter is 0.50 centimeters. So we can calculate the cross-sectional area. The permeability of low carbon steel is 2.5 times 10 to the negative fourth henries per meter, and we can find that in the index or the table in the back of the book. And again, those are numbers you can look up, or the problem may state give it to you. We'll use the inductance formula. L is equal to N squared times mu times A divided by L. And so let's do this step by step. So first, the number of turns. N is equal to 150. Plug that in there. Permeability, mu, is 2.5 times 10 to the negative fourth henries per meter. We'll plug that number in there as well. The cross-sectional area, A. So let's do some calculations. We have to go back to a little bit of geometry on this one. The radius is 0.25 centimeters, or again, remember I said converted to meters. So it's 0.0025 meters. And so area is going to be equal to pi r squared. I bet you thought you'd never use that formula again in engineering. And so we calculate the area, we're going to get 1.96 times 10 to the negative fifth meters squared. Now they're giving us the length, and we convert that to meters. The length is going to be 0.020 meters. And then we plug all these numbers in, or as my old math professor used to say, plug and chug. I don't even know where he got that from, but it never left me since the 80s. So let's plug those numbers in. L is equal to 150 squared times 2.5 times 10 to the negative fourth times 1.96 times 10 to the negative fifth. All of that divided by 0.02, we end up with an inductance of 5.52 millihenries. And what does this tell us? It's a number, but what does it mean? It shows how the number of turns and material properties dramatically influence inductance. A simple change to the core, say using ferrite instead of air, could increase inductance by orders of magnitude. This is why choosing the right geometry and core material is crucial for designing filters, chokes, transformers, and tuned circuits. So one more thing I want to add here, since we're at this stage of the game, is that you may get a job where you're designing circuits, and you also may end up getting a job where you're designing components. So think about that. Somebody has to design and engineer the components that we use to engineer the circuits. You might find yourself working in a manufacturing company that manufactures inductors. And this equation will save your life. All right, thank you very much, and let's go ahead and move on to the next topic. All right, everybody, let's talk about ideal versus real, the practical inductor model, right? The mathematical way of seeing it and the engineering way of seeing it. So far, we've treated inductors as ideal components, just a single L value that opposes current change and stores magnetic energy. But let's face it, real inductors are a little messier. Engineers, we get our hands dirty, right? Not just with pencil lead and eraser endings, we get our hands dirty. And here's the truth, no inductor is perfect. Every coil of wire has winding resistance, R sub W, that's denoted there because copper isn't a superconductor. It has winding capacitance, C sub W, from the electric fields between the coil turns. And these imperfections show up especially at high frequencies, where parasitic effects can shift your entire circuit's behavior. So let's look at the practical equivalent shown here. You've got your ideal inductance L in a series, right, where there's an R sub W, the winding resistance model of the resistance of the wire itself. In parallel, we add C sub W, representing the interturn capacitance that builds up between layers of the coil. And why does this matter? Well, because in real world circuits, R sub W causes power loss and voltage drop. C sub W allows high frequency signals to bypass the inductor, leading to unexpected behavior. This is probably not going to be a great comparison, but if you've ever been driving down the highway and you've got a traffic jam and some people go off road and go into the access road, that would be leakage current. Yeah, those people actually crossing and doing illegal things and going into the access road. C sub W allows you to do that. Together, they can form this unwanted resonant circuit, or in traffic, they can cause a lot of anger and aggression. Distorting signals here are creating noise. And again, in traffic, you will definitely hear a lot of noise when people cross the highway and go into the access road as they're crossing those grassy areas. And again, we don't want that, right? So that's why high performance inductors are wound with thicker wire to reduce resistance. Or on the highway, you might see those barriers to keep people from doing that. We have an engineering way to prevent those leakages. Wound, again, I said winding wire thicker, spaced or layered to minimize stray capacitance, and then sometimes shielding to contain those magnetic fields. So, and then I guess the shielding would be more like the barriers to keep the vehicles from going off and going into the side roads. Um, when you're designing filters, switch mode power supplies, or tuned circuits, don't just drop an L and walk away. Think of R sub W, think of L, and then think of C sub W, that capacitive leakage. And that's your real inductor. And again, one little uh, bit of foresight with C sub W. A major problem that we have in critical equipment that's sensitive to interference is called leakage current. So in medical devices, if you hook up a patient to a medical device and there's a conductor, there's a contact, it's actually making contact with the patient, you're forming the basis of what a capacitor is, and you get stray current leaking across that gap. And so we have to keep track of these things so that we don't actually electrocute patients. And believe it or not, this is with every device that you plug into an outlet. Your toaster, your refrigerator, your stove, every device has leakage current, and they should actually be checked annually to make sure that they're not leaking any more current because of that C sub W. And again, the C sub W I'm talking about is from the metal casing to the nearest ground outside of the ground that the device is hooked up to. Sometimes that can be a human being. And so we want to make sure that C sub W is extremely small for safety. But in this case, we're talking about C sub W because we want the signal to be nice and clean, and we don't want that signal interfering with the main signal that we want to transmit. All right. It's just an entire field of its own, leakage current and safety. Okay, now we can't forget Faraday. So let's talk about Faraday's law, the engine behind induction. So as we near the end of our discussion on inductors, it's time to revisit the foundation that ties all of this together, and that's Faraday's law. By the way, one more thing, I just want to promote Faraday. There's a documentary on Faraday's work. I recommend it. Any of the documentaries on Faraday are amazing. The work that he did to actually get us to this point. So any any documentary that you see on Faraday, I recommend you go watch it while you're in this class so you get a better appreciation of the work that you're working with. of the laws you're working with. All right, so anyway, this law is the heart of electromagnetic induction. So it's voltage induced times N times delta phi over delta T. And that's where VIND, right? V sub IND is the induced voltage. N, again, the capital N is the number of turns in the coil. And D phi, some people say phi, some people say phi for that symbol. Um, I better look it up and say it properly, but I'm going to just continue with my consistent pronunciation of it. Delta phi over delta T. You know what? I think it's phi. Delta phi. No. Yeah, I'll say phi. Delta phi over delta T. And this is a rate of change of magnetic flux. Um, so the takeaway for this is pretty simple. The faster the magnetic field changes and the more turns the coil has, the greater the induced voltage. The key word here is change. The constant magnetic field, you have no induced voltage. But when you ramp it up or you shut it down, boom, you generate a response. And this leads us straight into Lenz's law. Lenz's law tells us that the polarity of the induced voltage always acts to oppose the change in magnetic flux. So if current is increasing, the coil tries to resist by generating a voltage in the opposite direction. If current is decreasing, the coil fights to keep it going. It's, again, electromagnetic inertia. Coils don't like change. And this explains why you get a voltage spike when you turn off current to a coil, or inductors slow down current changes in power supplies, or maybe energy is stored temporarily in a magnetic field. It's all Faraday and Lenz at work. I want to make one other analogy to this. If you've ever played that game in school where they have the bean bags and you have to grab the little bean bag and run and drop it off in a little circle and you go back and forth. The thing that opposes your speed there is that the change in your direction. So you start off at one place, you run all the way to the other side, you grab the bean bag and you take it back to the other circle. I don't know if you know, all remember this little game in physical education, but you notice that the faster you go, the harder it is for you to stop and change direction. And so this is, again, that equivalent of the opposing change to energy in one direction. So maybe that'll actually help you contextualize this law. All right, now let's go ahead and continue with Lenz's law in action, right? So current resists the change. Let's take a look at Lenz's law, not just as a formula, but as a moment of dynamic resistance. This circuit helps us visualize exactly what Lenz's law means when current changes. So let's go ahead and break down this scenario. We have a voltage source denoted by V sub S, an inductor which is denoted by L, two resistors R sub 1 and R sub 2, and then we have a switch which is denoted by SW. And then the current meter. Initially, the switch is open, which means the current is flowing only through L1 and R1. And because the circuit is simple, the current is steady. The current behaves like a shorted wire, no opposition, no voltage across it. But here's where Lenz's law comes in. As long as current is constant, the inductor is passive. But the moment you try to change that current, whether by opening or closing the switch, the inductor reacts. It generates a voltage to oppose that change. And that's Lenz's law. That's what it tells us. Induced voltage always works against the direction of the current change. So in this setup, the meter shows a small current through R sub 1, but nothing happens yet because we haven't disturbed the current. In the next slide, we'll flip that switch and we'll see how that inductor actually responds. All right, just as I promised, we're going to close that switch. This is the second movie to Lenz's Law in Motion. The coil fights back. Right, in the previous slide, we saw a simple inductor circuit with an open switch. Now let's see what happens when that switch closes. This is where Lenz's law jumps into action. So the moment SW closes, the current wants to increase because now it has an easier path through both R sub 1 and R sub 2. But the inductor says, not so fast. That's because inductors resist, again, any change in current. And it doesn't matter whether the current is increasing or decreasing. The inductor reacts by producing an induced voltage across itself. The polarity of the induced voltage is opposite to that change. It creates a counteracting force that tries to keep the current the same as it was before the switch closed. And this is classic Lenz's law. We all say that. That's classic Lenz's law. Um, yeah, I don't know. That's what teenagers say. Oh, classic Lenz. The induced voltage, it opposes the cause of the flux change. And so in this case, the surge in the current. That's why the meter initially reads the same current, even though the circuit path has changed. The current doesn't jump instantly. Think of it again, or I'll remind you again, think of it like electrical inertia. A coil wants the current to ramp up slowly. It generates a reverse voltage to delay that increase, and eventually the inductor just settles and the current rises, but not without a fight. So this behavior explains voltage spikes again when you open a coil-driven relay, slowed current rise in power converters, and why inductors help smooth or limit fast transitions. It would make a great movie if we had a character who was an electron. We should do that. We should make a movie, and like they did Osmosis Jones, we should make a movie about a character who is an electron. Thank you. You heard it here first. All right, now welcome to the third movie, When the Coil Settles, in Lenz's Law in the Long Run, right? If this was a trilogy. So in the last two slides, we saw what happens when current tries to change and the inductor fights back, like the Empire Strikes Back. I just thought of that. Just kind of made a connection. Anyway, now let's go ahead and fast forward a little bit in time. So what happens after that initial opposition fades? Okay, good. The answer is the current eventually stabilizes, but at a higher level than before. So in this final diagram, the switch remains closed. The current flows through both R1 and R2. At first, the inductor again opposes the change with an induced voltage, but over time, as the current settles into a new steady state, the magnetic field becomes constant again, and when that field stops changing, the inductor no longer resists. The induced voltage across the inductor decays to zero, and it acts like a simple wire, just part of the circuit now. And what's the result? The total current increases, and the meter shows a higher reading than before the switch was closed. And that's because the total resistance has decreased. The current now flows through R sub 1 and R sub 2 that are in parallel. This offers a lower resistance path, and this perfectly illustrates transient behavior in inductors, excuse me. The initial opposition to current change, exponential voltage decay, and final equilibrium, that's where the inductor's only role is in resistance, if any. Understanding this is useful and it helps explain relay delays, that rhymes, I didn't mean it to rhyme, inrush currents, and why you can hear that click or snap when switching inductive loads. Now, this also explains why Star Wars, the first trilogy, was awesome because they followed these laws. The prequels were awesome, and that trilogy was awesome. And then in that last, I don't know what it was, I think Star Wars developed a short, and they completely missed the point of the Force. All right. Um, yes, now you know how I feel about that trilogy. Let's keep on going to the next slide. As usual, let's talk about practical inductors from theory to the toolbox. We've talked about inductors in theory, magnetic fields, formulas, Faraday, and Lenz, but what do they actually look like in the real world circuits? Well, they look like Star Wars 1, 2, 3, 4, 5, and 6. Star Wars 7, 8, and 9 is when you had a short circuit or something wrong with the circuit. Sorry, I'll get back to lecture. Right, so what we see here in the slide, it shows you that you have a lineup of practical inductors, right? The components you'll find on benches, breadboards, and inside commercial electronics. So let's go ahead and meet them. We have the encapsulated inductor. That's a general purpose inductor. The wire coil is sealed in an insulated case. Common in signal filtering, RF circuits, and small scale power supplies. They're often color coded like resistors. We also have wire wound. These are high current inductors. They're made with thicker wire and often air or iron cores. They handle larger currents without overheating. They're found in power conditioning chokes or buck converters. We also have the toroid coil, kind of hard to say, toroid coil. And that's a donut-shaped magnetic core with wire wound around them. This is a tongue twister, wire wound around them, right? It's excellent for low electromagnetic interference. You know it as EMI. It's used in high frequency power supplies, filters, and in audio systems. And what it does is it shapes confines that magnetic field inside the core and it reduces external noise. You also have shielded inductors, as shown there in the rectangular metal housing. That's often part of an RF or a switch mode circuit where EMI shielding is essential. The metal case prevents field radiation, making it ideal for dense PCB layouts. Then we also have, as usual, the variable inductor. And this has a movable core, or what they call a tunable coil. You can just adjust the inductance by rotating a screw or sliding some ferrite core. These are found in oscillators, tuners, and radio frequencies where precision matching is needed. So if you remember those old radios where you're turning the knob, you are actually turning or tuning an inductor inside that circuit to allow a certain frequency to come in and filter out the other ones. Same way the older televisions worked as well. Now you just hit a little button and we kind of forget how radio waves actually transmit through space. So that's kind of like the big takeaway. Each of these components, they perform the basic job, the same basic job. They store energy magnetically, they oppose changes in current, all of them do that, but they're built for different environments. So tiny signals or big currents, high precision or high power, EMI sensitive or robust and simple. The right inductor makes your circuit more efficient, more stable, and more responsive. And this will be my last comment on Star Wars. They had a fantastic actress, and I thought she was going to do an amazing job. I saw the trailer, and again, it had nothing to do with the component that they chose for the movie. It had to do with the designer of the circuit or the designer of the story. And again, this will be the last Star Wars reference I make. If you like the last three movies, good for you. I um, hopefully they'll recover from that. Thank you. Okay, now let's talk about what happens when we connect inductors together. And we're going to talk about how we connect inductors in series. What does that do? So connecting inductors in series or adding magnetic resistance, basically. Let's say you need more inductance than a single coil can provide. What would you do? Just like resistors, you can connect inductors in series. And the rule is just beautifully simple. When inductors are connected in series, the total inductance is the sum of the individual inductances, right? Sounds very familiar to resistance. So mathematically, L sub T or L sub total is equal to L1 plus L2 plus L3 plus, and you'll see dot, 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 all the way to L to the N. And this assumes that the magnetic fields from each inductor don't significantly couple, right? So you're treating them as independent energy storage devices. So let's go ahead and look at this example on the slide. You have one inductor at 1.5 millihenries. You have another one at 680 microhenries. Again, pay attention to the prefixes. 680 microhenries ends up being 0.68 millihenries. Again, it's just making the number look different, but it's the same value. And then we add those together. L sub t, again, or L sub total, which that's what T means, is equal to 1.5 millihenries plus 0.68 millihenries. And adding those together gives us 2.18 millihenries. And that's it for adding inductors in series. No different than adding resistance in series like resistors. Very straightforward formula. Um, yeah, that's it. So like just with magnetic opposition, but instead of electroresistance. So why use inductors in series? Uh, let's say you want to build a custom value from standard parts. So I don't know if you know this from your past classes. The resistors that you have in your lab and most of the resistors that you see are called they're standard values, meaning they manufacture these things by the millions. And we don't have every single value of resistor available. But if you needed a custom resistance for a particular circuit to work optimal, you'll build a circuit to give you that equivalent resistance. So we do the same thing with inductors. We can't manufacture every single value. And so with just these values, we can pretty much combine them and make an equivalent inductance to get the one we need if we need something extremely specific. Right? Sometimes you do get that. So sometimes you will find things that are not standard values, and manufacturers will build something for someone, maybe a resistor that is very, very specific. It's a value you just can't buy off the shelf. And that might be just to kind of simplify the design or make the design even smaller and more compact. And so you just can't easily take that component out and replace it if it ever burns out. This is when you have to actually go back to I will say the manufacturer and order that exact same resistor or that exact same inductor. So to combine different core materials, you can also do this to give you different inductances. And then let's say you want to isolate parts of a circuit magnetically while you still want to influence the current behavior. So one thing to note though is when you wire inductors closely in series, you have something called mutual inductance that may come into play. And that's when their magnetic fields interact with each other. So you may need to adjust for coupling effects. But in general, series inductance just adds up. All right, we talked about series inductors. Now let's go ahead and talk about parallel inductors, right? Less is more. Resistance to change. So I hope you like my titles, by the way, for each slide. We just saw that inductors in series add up. More coils, more inductance. But what happens when you wire inductors in parallel? We might have something familiar to relate to. The result is very different from series, right? So the total inductance ends up decreasing, and it's always less than the smallest individual inductor. Does this start sounding familiar to another component that does this? And here's the general formula. If that doesn't kick in any memories or get your memory cells to actually, uh, remind you for inductors in parallel. So 1 over total inductance, so 1 over L sub t is equal to 1 over L sub 1 plus 1 over L sub 2 plus 1 over L sub 3 plus dot, 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 all the way to get to L sub and however many inductors that you have. And this is called the reciprocal sum, just like resistors in, you guessed it, parallel resistors, right? And for just two inductors, it simplifies to total inductance equals product over sum. Does that sound familiar? L sub 1 times L sub 2 divided by L sub 1 plus L sub 2. Remember, this is a special case when you have two of these only. It only works for two. If you have three inductors, you have to go back to the reciprocal sum, just like in resistors. Inductors do the same thing. The mathematics is the same, which is why we can do the same similar formula. Again, we call this last one, L sub t is product over sum, L sub 1 times L sub 2 over L sub 1 plus L sub 2, product over sum rule. And it gives you a quick shortcut in common designs. So why does inductance drop in parallel? Because each coil provides an alternate path for current to build a magnetic field. So more paths, less overall resistance to change. The magnetic energy is now distributed between multiple coils, and the net effect is a lower overall inductance. The practical reasons to use parallel inductors, or maybe you want to reduce overall inductance, to share current load across components, and maybe to fine tune circuit responses, especially in RF or tune filters. So just remember this, if you're combining inductors that are close together, mutual inductance can influence the total. So always take spacing and coupling into account in your design. Okay, I had two titles for this slide, parallel inductors, you do the math, or parallel inductors, let's do the math. You choose. Anyway, you can keep them both. So now that you've seen the theory behind inductors in parallel, let's work through a practical example because this is where it really sticks. So in this slide, you're given L1 is equal to 1.5 millihenries. L2 is equal to, again, 680 microhenries, and we convert that to millihenries. 680 microhenries would be 0.68 millihenries. Again, these inductors are connected in parallel, and we want to find the total inductance, L sub t. So we can use the product over sum for just two inductors. Remember, it's L sub t is equal to L1 times L2 divided by L1 plus L2. So just go ahead and plug in the numbers. 1.5 times 0.68 divided by 1.5 plus 0.68, and we end up with 0.468 millihenries, or if we want to go back to your original units, 468 microhenries. And that's your answer, 468 microhenries. So notice how it's less than either of the two values individually, just like in the parallel resistor comparison that we had starting from last semester. I shouldn't say semester, just the last time we talked about resistors. And why might you wire inductors this way? This is kind of an important question for design. Again, to reduce total inductance without buying a single smaller inductor, to share current across components and improve thermal performance, or maybe to fine tune circuits response time or filter bandwidth or resonant frequency. Again, another thing to keep in mind here is for accurate results, the inductors should be physically separated or shielded to avoid mutual inductance skewing that outcome. All right, inductors in DC circuits, the art of slowing things down. So it's important to understand how this thing works when it's initially exposed to a change in voltage, right? So we call this the step response. So we've looked at how inductors behave in AC and ideal scenarios, but that's a little deceptive and it's a little deceptively simple. What happens when you connect an inductor to a DC source? So you might think the response would be immediate and boring, but with an inductor in the mix, it's anything but that. And so let's talk about this setup. You have a DC source, V sub S here, that's connected in series with a resistor, let's say R1, and an inductor L. And at the moment that switch is closed, you might expect the current to instantly jump up to V sub S over R. But inductors don't play that way, at least not in classical physics or in our universe, unless we're discussing maybe quantum inductors or something that doesn't exist, where two things can actually exist in the same point, in different points in the same time, right? So that's why we don't have instantaneous anything here in the real world. But because inductors resist change in current, the current rises exponentially, not instantly. So at T0, the inductor sees a sudden change. It generates an opposing voltage. The voltage across that inductor is maximum at the start, and then it decays to zero. The current starts um, at zero and then gradually increases up until it stabilizes. And we see this in the graph there on the slide. The top graph shows voltage across the inductor dropping exponentially after the switch closes. The bottom graph shows current through the inductor increasing smoothly over time. And this behavior is defined by what's called the time constant. We designate time constant by the symbol tau. It looks like a fancy little t, or a fancy little capital T, however you want to describe it. It's the Greek letter tau, and it's calculated by inductance divided by resistance, where L is the inductance in henries and R is the resistance in ohms. And then that little fancy T, tau, is the time it takes the current to reach about 63% of its final value. So let's go ahead and summarize what we have here. Inductors don't stop DC. They just slow the rise of current when DC is first applied. And once the current stabilizes, the inductor behaves like a short circuit. And the principle in this essentially is that it it provides surge limiting, it helps in switching converters, and helps with power up sequencing, like in digital systems. Square waves and switching inductors, energy on the move. Okay, I'm also going to give you the title of my slide. Cool title. All right, we've seen how inductors respond when a DC source is suddenly applied, but what happens when that voltage keeps switching? That's exactly what this slide explores, the behavior of an inductor in a DC circuit with a square wave source. So think of it as either a switch opening and closing, but basically providing that square wave. Let's go ahead and break that down. If we have a square wave voltage source, V sub S, and that's feeding a series RL circuit, the waveform flips between on and off, basically, applying the step voltage over and over and over. This rapid switching, it's common in pulse width modulation, switch mode power supplies, and digital control systems. And what does the inductor do, or what is the inductor doing? Let's take a look at that voltage in the graphs. V sub R, which across the resistor, that follows a curved exponential rise and fall. And that's because current through the inductor ramps up and down gradually, even though the voltage flips instantly. V sub L, the voltage across the inductor, this shows a sharp spike and dips, right? And that's when the square wave jumps. The inductor fights back by generating a large opposing voltage that's in line with Lenz's law. And what this means is that the inductors smooth the current and sharpen the voltage response. But in practice, this behavior it filters noise in signal paths. It controls power delivery in converters. It prevents current surges in switching circuits. And one thing to remember is that these same curves mirror what you saw with the DC step source, but it's just repeated and flipped. Now let's go ahead and move on to the universal exponential curves, timing and the rise and fall. So let's go ahead and zoom in on one of the most important timing concepts in RL circuits, and that's the exponential response. So whether you're looking at current rising or voltage falling, inductors always shape these changes with a very familiar curve, and it's governed by the time constant, which remember we said was symbolized by tau, or that little fancy t. Um, in an RL circuit, the time constant we define it as tau. I got to enunciate that. Tau is equal to L divided by R, right? Inductance divided by resistance, where L is inductance in henries and R is resistance in ohms. Tau tells us how quickly the circuit responds. It's the time it takes for a signal to change by about 63% of its final value. Current building up in an inductor after you close a switch, you can track progress. So for 1 tau, so the very first tau, the increment, current reaches 63%. By the time you get to 5 of those time increments, or 5 tau, the response is considered effectively complete. It's 99.9, it's really, really close to 100%, and it's 99.99%. Um, and so it's close enough, right? We can keep going and say 99.9, 99.999 something, but at the fifth time constant, we're there, right? So for a falling exponential, such as the voltage across an inductor collapsing after a switch opens, you'll see again 1 tau with the voltage being dropped to 37%. Now realize here that if we're rising, it's 63%. If we're dropping, it's 37%. A good way to remember these is that both of those have to add up to 100%, right? So 63 and 37, that makes 100. By 5t or 5 tau, it's down to just 1%, right? On the other side, it was up at 99%. So 99 and 1%, that should equal 100. What these curves are called are is universal because they apply to any inductor resistor combination. Once you know tau, you can predict the whole response over time. And what this does is that it helps you design circuits with controlled rise and fall times, predict transients in power electronics, shaping timing in filters, relays, and signal conditioners. All right, let's move on to reading the curve when one voltage overtakes another. So let's use what we've learned about exponential curves to extract real insight from a dynamic RL circuit. And here's the question. In a series RL circuit, when is VR greater than 2 times V sub L, or VL, right? In other words, how long does it take for the voltage across the resistor to significantly overtake the voltage across the inductor? Think about it like this. VR follows the rising exponential. VL, or V sub L, follows the falling exponential. The moment we're looking for is when VR is greater than 2 times that of V sub L. And that happens when VR reaches 67% of its final value. Why? Because when VR is 67%, V sub L is 33%, right? They have to equal 100. You can't have more than that. And that's a ratio of 2 to 1. So looking at the universal curve, we find that this point occurs at approximately 1.1 time constants, or tau. So after 1.1 tau, the resistor voltage becomes twice the inductor voltage. And why is this important? Because it shows how you can use a universal curve without doing complex math. And I know a lot of us love complex math. So we'd use it for time circuit responses to predict when control thresholds will be crossed, and designed for precise voltage division or energy transfer rates. And this is especially useful in circuits with switching elements, relays or solenoids, or control loops that rely on time-based behaviors. All right, let's go ahead and talk about graphing the curve. I normally don't like to do these slides because this is very specific to Texas Instruments, and I don't like to promote a particular product. I personally use HP calculators. They were the older engineering calculators designed for us. But I'm going to go ahead and do it just to be thorough here. So graphing the curve, plotting exponentials on your calculator. Most of you might have a TI if you have any kind of calculator. If you really want to understand exponential behavior in RL circuits, again, don't just read about it, plot it. This slide is going to show you how to use the TI-84 plus CE specifically. It might be very similar to the other TIs. I don't know. I'm not a TI user. But if it is, good. If not, just find a TI-84. You can actually also download the TI-84 app. There's an app for this, so you don't actually have to buy that calculator. This is an older calculator, and yeah, if you want to see the function, just download the free app and then follow along the directions. It's an emulator, so it looks just like the real calculator. Again, you can use any graphing tool to visualize these rising and falling exponentials for RL circuit analysis. So the two normalized equations are the rising exponential and the falling exponential. The rising exponential is the following: y is equal to 1 minus e to the negative x. And this models a voltage or current building up over time, like current in an inductor after a switch closure. The falling exponential is y is equal to negative e to the negative x. And this represents a decaying response, like inductor voltage dropping off after power is removed. These curves don't require any specific values for L or R. They're normalized using the time constant. That's why the curve is called a universal. The calcular settings shown on the slide here give you the perfect view. So x min is equal to 0, x max is equal to 5.28, and that covers 5 tau, or 5 time constant. The y minimum is equal to 0, and the y max is equal to 1, and that shows the percentage from 0 to 100, 100%. So you'll see the classic S-curve rise for the y is equal to 1 minus e to the negative x, and the smooth exponential drop for y is equal to negative e to the negative x. And with these plots, you can predict circuit behavior, analyze time thresholds, visualize how fast your inductor catches up or lets go. And this is especially useful in labs or design where you don't have time for full simulation, but still want to anticipate the behavior of your circuit over time. So at a glance, reading values on the universal curve, if we take a moment to see how universal exponential curves can give you fast, accurate results without solving equations every time, you've seen how we graph rising and falling exponentials on this TI-84, what we see here on the graph. We're using the graph to find specific circuit values at any moment in time. Our focus right now, let's see, is on the rising exponential, so y is equal to 1 minus e to the negative x. And we're asking ourselves this question: what's the value at x is equal to 2? So if you look at the graph on the calculator screen, at x equal 2 time constants, the y value is approximately 0.8647, or 86.5% of that final value. This tells you that in an RL circuit, after 2 tau, or 2 time constants, the current or voltage across the resistor has reached about 86% of its final steady state value. The inductor voltage, if you're watching that, that has fallen to 14%. Now again, remember that whatever is falling and whatever is rising, both of those at any point have to equal 100%. And then why is this useful? Because now you don't need to memorize a full exponential function or punch in long equations. Just remember that at 1 tau, remember that's one time constant, it rises to 63%. At 2 time constants, it's 86%. At 3 time constants, it's 95%. And then when you get to 5 time constants, it's 99.99 something. What we say it's effectively done. We say it's 100%, but it's very, very close. Close enough. And these numbers give you quick checkpoints for real-time design decisions. So when is a relay fully energized? How long until a filter reaches its target value? What delay should I expect in a power ramp up? Um, so with just one equation and a few landmarks on the curve, you can predict, design, troubleshoot with some confidence. Okay, let's go ahead and move into the general formula. Don't let that long formula worry you. I was going to say scare you, but yeah, I'll go ahead and say it. Don't let it scare you. That general formula, it's used for predicting every point on the curve. So again, we're wrapping up our study of universal exponential curves, and it's time to give you that master formula, the one that describes the instantaneous current at any point in a first order RL circuit. So the general formula is I of t is equal to I sub f plus, and then parentheses, I sub I minus I sub f times the exponent e raised to the negative RT over L. So let's go ahead and talk about what each one of those variables mean. I sub t is the current at any particular time, right? You might know that from algebra, how to read that. I sub I is the initial current at 0. I sub F obviously is the final, that steady state current. R is the resistance in ohms, and L is the inductance in henries. And the factor e raised to the negative RT over L, that's the exponential term tied to the circuit's time constant. What does this formula do? It blends the starting and ending points of a current transition. It's based on how much time has passed and the circuit's L to R ratio. So you get a precise current value using this formula instead of an approximation on the graph. You can use this for rise behavior when the inductor is energizing, decay behavior when the field is collapsing, or switching conditions in digital loads, motor wind down, or solenoid release. And conceptually, if you think about it, if I sub F, the final current, is greater than I sub I, that means that the current is rising. So you have a field that's building up. If I sub F is decreasing, I'm sorry, if I sub F is less than I sub I, the current is falling, and so your field is collapsing there. Either way, the exponential term decays over time, and then I sub I of t transitions smoothly. So after about 5 time constants, or 5 tau, the exponential term gets so small that I of t is approximately I sub f, and the transition is complete. So the next time you flip a switch and you see a current change, remember this. There's a formula for that, and it's beautifully predictable. Now, to give you another, I like to throw in a bunch of other bits of trivia that you might not know. These decay constants, I mean, these decay curves um, these general formulas are not just for current. We actually use these same type of equations when we're trying to predict, let's say, a pandemic, and we're trying to look at the spread and the rise and fall of infected individuals. So this is a very standard formula that you use in a bunch of different places in science and in biology. So it's very important to understand this concept, not just the formula, and you'll find that you can apply this to so many other um, different scenarios. It's not just for current. But again, that's for another class. Inductive reactance, AC's magnetic obstacle. So up to now, we've talked about how inductors respond to changing current and how they behave in DC and transient conditions. But what happens in steady state AC circuits? That's where we bring in the concepts of inductive reactance, the frequency dependent resistance that an inductor offers to alternating current. And the formula for that is X sub L is equal to 2 times pi times F times L. And that's where X sub L is inductive reactance. That's going to be in ohms. F is in frequency in hertz. L is the inductance in henries. And the key idea is the faster the signal switches direction, the harder it is for current to get through the inductor. Because inductors oppose change, higher frequencies mean more change per second, which means greater reactance. Let's go ahead and break down the examples we see here on the slide. So example A says you're given L is given to you at 33 millihenries. The frequency is 550 kilohertz, and we just plug those numbers into the formula. X sub L is equal to 2 times pi times 550 kilohertz times 33 millihenries, and you plug all that into your calculator, you should get 114 ohms, right? So that inductor behaves like a 114 ohm resistor at 550 kilohertz, but only for AC. It would be nearly 0 ohms if we were just using DC. Let's go ahead and look at example B. We're going to go ahead and reverse this. You're told desired reactance. You want to get something that's 10 kilo ohms, or responds like it's like a 10 kilo ohm resistor. We have a frequency of 40 megahertz, and you want to solve for the inductance. So we can rearrange that equation. So L is equal to X sub L divided by 2 pi F. So we plug in the numbers, 10 kilo ohms or 10,000 divided by 2 times pi times 40 times 10 to the 6, and we're going to get 39.8 microhenries. So to achieve a 10 kilo ohm of impedance at the frequency, you need a 39.8 microhenry inductor. That's a very typical value for RF circuits. Inductive phase shift. So why voltage leads the way? Let's close out our deep dive into inductors with one final and critical concept in AC analysis, the inductive phase shift. So when a sine wave is applied to an inductor, something interesting happens. Interesting to me and interesting to the electron. Voltage doesn't rise and fall in sync with current. Instead, it leads the current by exactly 90 degrees. Look at the waveform on the slide. The voltage across the inductor, VL, V sub L, hits its peak before the current does. The current waveform lags the voltage by a quarter cycle, or pi over 2 radians, or 90 degrees. This happens because of how inductors respond to change. Voltage across an inductor is proportional to the rate of change of current. So when current is increasing the fastest, voltage is highest. When current is at its peak, meaning it's not changing at all, voltage is zero. The relationship is not just academic, right? It affects power calculations, power factor correction, circuit resonance, And the behavior of RL filters, chokes, and reactive loads, if you ever wonder why your oscilloscope shows one sine wave ahead of another, it's because of that phase shift behavior. And if you haven't observed that yet, you will when we're dealing with labs and pertaining to this section. And then a final rule of thumb. In a purely inductive circuit, voltage leads current by 90 degrees. And this is the exact opposite of what's going to happen in a capacitive circuit when we talk about that, where current leads voltage. Understanding this phase relationship gives you the insight to analyze, to tune, and help design circuits with timing and energy flow in mind. All right, power in an inductor, real versus reactive. Let's finish our journey through inductors by clarifying a key concept, how power behaves in an inductive component. And here's the headline. Ideally, inductors don't consume power, they just store and release it. But in the real world, things are a little bit more nuanced, right? We're not mathematicians. We have to deal with real world consequences. So first, let's talk about true power. Even though inductors are energy storage devices, they're still made up of wire, and the wire has resistance, and that resistance is represented by R sub W, and it causes a small but measurable power loss, especially when current is high or the coil has a lot of turns, many turns, or the wire is thin or poorly ventilated. So the formula for true power loss in the winding is P sub true, right, or P maybe sub T, depending on the textbook, is equal to I sub RMS squared, so the RMS current squared, times the winding resistance. I'm going to go ahead and repeat that again. You're looking at the formula on the slide, but just want to make sure I say that. True power is equal to current RMS current squared times winding resistance. And this is the real power the inductor dissipates. It's turned into heat, just like a resistor. So let's go ahead and talk about reactive power. Reactive power is not consumed. It's cycled back and forth between the inductor and the source. So reactive power, it's the rate at which the inductor stores magnetic energy and then returns it to the circuit. So the equation for that is P sub R is equal to VRMS times IRMS, right? So voltage times current, if you remember the power formula. But remember, this isn't real power like in a heater or a light bulb. It's VAR or volts amp reactive, and it's not watts. What does that? Why does that matter, right? Because power systems, motors, and AC circuit designs, they account for true power, which is in watts for energy consumption, and then reactive power, VARS or V sub ARS for energy movement. And apparent power, which is going to be denoted as V sub A or VA, this is a combination of both. Inductors will increase reactive power demand, and that can affect anything from power factor correction to transformer sizing. All right, the Q factor, and I'm not talking about Q from Star Trek, even though Star Trek is a phenomenal space exploration show, which Star Wars used to be a great show about space. Again, this is the last slide I'll ever mention Star Wars, maybe. Right. So the Q factor. How sharp is your inductor? We're going to wrap the study of our inductors with one final metric that tells us just how good your inductor really is. And again, we call that the quality factor, or we just call it Q. Um, the Q factor, right? A measure of efficiency in the inductor. It tells us how well the inductor can store energy reactively without wasting it as heat. Mathematically, again, we deal with this mathematically first. Q is the ratio of reactive power to true power. So you look at the equation there, Q is equal to I squared times X sub L, which is the equivalent of impedance, right, divided by I squared over the winding resistance, R sub W. So the current I cancels out, which just simplifies this formula to the impedance, which is X sub L, divided by the winding resistance, which is R sub W. So X sub L inductive reactance, again, that increases with frequency or it's frequency dependent. R sub L is just that winding resistance. That stays relatively constant. The higher the reactance and the lower the resistance, the better Q. And again, why does this matter? Because it gives you insight into energy efficiency. It also gives you an insight into bandwidth of resonant circuits. It can tell you how sharp or selective a filter or a tuned circuit is going to be. So a high Q That sounds like IQ. I gotta make sure I enunciate these things. A high Q inductor stores energy efficiently and has narrow bandwidth, which is ideal for things like RF coils, audio filters, oscillator tanks, and a low Q. Again, I'm not saying low IQ. I'm saying low Q inductor is lossy, right? Lousy and lossy. It dissipates too much power as heat. One important thing to note for this whole thing is that Q is frequency dependent because of X sub L, right? X sub L is equal to 2 pi F times L, and we got that F in that formula. So it's frequency dependent. So when you report a Q value, it's always at a specific frequency, just like reactance or impedance. If you're designing for signal fidelity, narrow band filtering, or resonance, you want a high Q coil. If you're just choking noise or smoothing current, Q may not matter so much, but it still tells how efficient your inductors is under AC. Now, this is something that I deal with, or I used to deal with quite a bit, because even though I say I'm a clinical engineer, I deal with instrumentation. And so dealing with instrumentation where signal quality, especially with variation of signal quality, I'm sorry, I'm saying that correctly, where signal is oscillating. We don't have sine waves, obviously, in the body, but we do have fluctuating signals. Having a high Q is actually very, very important. It's important for other fields as well. I'm sure in aviation, it's super critical, but in the medical field, it's also super critical. All right. All right, so this concludes this lecture. Again, I'm going just to go ahead and give you a review, talk about the key terms that we discussed. You can follow along in the slide or you can just listen, right? So first we talked about the inductor, an electrical device formed by a wire wound around a core, having the property of inductance, also known as a coil. And again, I'll just be reading the slide here. We talked about winding. That's the loops or turns of wire in an inductor. We talked about induced voltage, the voltage produced as a result of a changing magnetic field. Then we mentioned inductance, the property of an inductor whereby a change in current causes the inductor to produce a voltage that opposes a change in current. Some more terms that we discussed in this podcast are the Henry, denoted by the symbol H. And this is the unit of inductance. The RL time constant, a fixed time interval set by the L and R values that determines the time response of a circuit. It equals the ratio of L divided by R. So that's the formula for time constant, L divided by R. Inductive reactance, the opposition of an inductor to sinusoidal current. And the unit of that is in ohms. And then we ended up with the quality factor, the ratio of reactive power to true power of an inductor. All right, and now it's time for our quiz. Don't forget to pause after I ask the question and try to answer the question before you continue. Okay, so question number one, assuming all other factors are the same, the inductance of an inductor will be larger if what? A, more turns are added, B, the area is made larger, C, the length is shorter, or D, all of the above. And I'll go ahead and say pause the video right here. Okay, so if you pause and you came back, the answer for number one is D, all of the above. Question number two. The Henry is defined as the inductance of a coil when A constant current of 1 amp develops 1 volt, B, 1 volt is induced due to a change in current of 1 amp per second, C, 1 amp is induced due to a change in voltage of 1 volt, or D, the opposition to current is 1 ohm. Go ahead and pause the video. Okay, if you're back, the answer is B. 1 volt is induced due to a change in current of 1 amp per second. This is question number 3. The symbol for a ferrite core inductor is, again, there's no way for me to read anything here. I'm just going to give you the choices. Is it A, B, C, or D? Go ahead and pause the video. Okay, if you start the video again, the answer is D, right? It's got that little coil with the little dashed lines up on top. Okay, this is quiz question number 4. The symbol for the variable inductor is, again, I can't describe these, A, B, C, or D? Let me try to describe them. A, the little squiggly line with nothing inside of it. B, the little squiggly line with a thick bar and a thin bar on top of it. C, the little squiggly line with an arrow through it. Or D, the little squiggly line with a dash arrows above it. That's probably the best I can do. Go ahead and pause the video. All right, if you return from the video, the right answer for number 4 is C. A variable inductor is that little squiggly line with the arrow through it, kind of like the variable resistor. Okay, I'm going to go ahead and read this one the way it's written, and you'll see why. Quiz question number 5. The total inductance of a 270 microhenry inductor connected in series with a 1.2 millihenry inductor is what? A, 220 microhenries, B, 271 microhenries, C, 599 microhenries, or D, 1.47 microhenries. And I'm not going to pause this video. I'm going to go ahead and explain that none of the answers are correct. This is a typo from the publisher. So again, I've submitted this correction so many times. Again, if you had a 1.2 millihenry inductor and you're adding another inductor in series, the answer has to be something greater than 1.2 millihenry. And none of the answers shown there are greater than 1.2 millihenry. So either D was intended to be the right answer and they forgot to they put micro instead of milli, or something else. But I would guess that the right answer should have been D, 1.47, but instead of micro, it should be milli, the little m. I'll try to draw it and hopefully you can see it. All right, question number 6 of the quiz. The total inductance of a 270 microhenry inductor connected in parallel with a 1.2 millihenry inductor is, I'll go ahead and pause the video. All right, hopefully you're back and you've calculated this using the product over sum. And the correct answer is A, 220 microhenries. Quiz question number 7. When an inductor is connected through a series resistor and switched to a DC voltage source, the voltage across the resistor after the switch closes has the shape of what? A, a straight line, B, a rising exponential, C, a falling exponential, or D, none of the above. Go ahead and pause the video. All right, if you're back, the correct answer is B, a rising exponential. Question number 8 for the quiz. For the circuit shown below, the time constant is what? A, 270 nanoseconds, B, 270 microseconds, C, 270 milliseconds, or D, 3.7 seconds. Go ahead and pause the video now. All right, if you're back, the correct answer listed is 270 nanoseconds. Question number 9 for the quiz. For circuit shown, assume the period of the square wave is 10 times longer than the time constant. The shape of the voltage across L is A, the triangle wave, B, the exponential rise and fall, C, that sharp rise and exponential fall, and then flipped inverse into the negative direction and exponential rise, or D, that square wave pulse. Go ahead and pause now. All right, if you're back, the correct answer is C. Finally, question 10 of the quiz. If a sine wave from a function generator is applied to an inductor, the current will what? A, lag voltage by 90 degrees, B, lag voltage by 45 degrees, C, be in phase with the voltage, or D, none of the above. Go ahead and pause the video now. All right, if you're back, the correct answer was A, lag voltage by 90 degrees. Okay, so this is the answers for the previous quiz we just took. You can compare your answers to what you got. And I want to thank you very much for your time.